Okay, cool.
Please give a quick background about yourself and about the work as well.
So my name is Romain Fontugne. I'm Deputy Director at ISJ Research Lab. ISJ is an internet service provider in Japan, so I'm here in Tokyo. And I lead a project called the Internet Health Report. My research is mainly about internet measurement, and as Amreesh said, I was 2 years ago as MANRS ambassador, and last year I was MANRS mentor. So the work I will present was during my when I was MANRS ambassador. Share the slide. Okay, and so this was a project where we are interested in RPKI, and we wanted to see how much time it takes for the RPKI data to propagate on the internet. Let me just track the time. Okay. So I guess here the audience is pretty much aware of RPKI, but I will do just like a brief summary. So RPKI is more or less our best chance to secure BGP. You can see RPKI as a database where you put, where we have signed objects, digitally signed objects. And currently the most common object we have in RPKI are called route origin authorization, or ROA. And a ROA just tell us which AS is authorized to announce a prefix. And this information is used by certain ISPs that implement route origin validation. So route origin validation, or ROV, is when a router gonna receive a BGP route from route from BGP, and it can check in RPKI if that route is legitimate or not. So usually we say there is like 3 different classifications that are possible. Either the route is valid, that means the route that is seen on BGP match the information we have on RPKI. It could be invalid, so the route is not matching, and the router that implements ROV will usually drop this route. Or it could be not found, means just that the route is unknown in the RPKI database. So this is the basic of ROV. I'd like to give a bit more detail because that study is trying to understand how fast is the RPKI data available for ASCs that implement ROV. So as I said, there is to do ROV, you need 2 types of data. You need BGP data and RPKI data. So here in this figure, you can see the green ASCs here are implementing ROV. They will obtain BGP data from the topology. So the BGP data is just pushed over the topology when an AS announces a prefix. That information will be propagated to this the AS peer, and that's gonna propagate like that through the entire internet. So this is how BGP gonna propagate on the network. And when an operator announces a new prefix, if that operator is also using RPKI, now the operator also has to add a new ROA in RPKI. And to do that, the most common way is to use the IR portals or their API. And the operator will just query the IR to create a ROA. On the IR side, there is a software called the Certificate Authority that will create this signed object. And then this will be pushed to a repository called the publication point that make this ROA available for anyone. So the network that implement ROV, they will go to this publication point, download the new information. To do that, they have a piece of software called a relaying party. And so that relaying party will come every, so this is set by the operator, but it could come like every 15, 30 minutes or 5 minutes. It really depends on the operator, what the operator set. The relaying party gets the new ROAs, read this, make sure that everything is fine, and then it will push this information to their routers. So then the router can use that new ROA to make its routing decisions. And so what we're interested in this research is to understand the timing of all this operation. For BGP, there's a lot of studies that are done already. It's pretty well understood. Most BGP operation will converge and propagate on the internet in less than a minute, so it's pretty fast. But for RPKI, we don't really know. RPKI wasn't really designed with fast in mind, but now because a lot of operators are using this, it's very important to understand this, because that could be a bottleneck also for like quick operations. So we want to know how long it takes when we create a ROA, how long it takes for that information to propagate through the area, and for the ISP to fetch this and to give that information to their router. How does it compare to BGP? Is it in the same order of magnitude, or is it really different? And again, that's an important information for operators, so they can expect a certain timing for their operation. So to answer those questions, we've set up, in fact, 2 experimental setups. I will have time to explain only one. What we've done is we obtained from the 5 RIRs, we obtained experimental prefixes. And in the first experiment we've done, we announced these prefixes from an experimental AS that has a single upstream. This upstream is not doing ROV, but the 2 upstream of our upstream are doing ROV. So this entity and Spirit here are implementing ROV. And this network is also appearing with a few other networks on the Seattle Internet Exchange. Okay, and we did that experiment. The experiment I'm gonna explain, we did it for almost a year. And the experiment consists of these RPKI beacons. So we call these RPKI beacons. The way it works is first we are announcing our prefixes on BGP, and we're gonna create a ROA that makes it invalid. So our 2 upstream, entity and Sprint, gonna drop this, and that announcement won't be, actually the BGP announcement won't be visible globally. Then we start this beaconing. It's written like ROA toggling here. The beaconing consists of, first we create a ROA that will this time make the announcement valid. So now the prefix will become reachable. We know when we create the ROA, so we can check in some data source like BGP or Traceroute when this become reachable. We are waiting for some time, about half a day, and then we're gonna delete that ROA. So the ROA we created in the first step. So the prefix will become invalid again, the announcement will become invalid again, and we expect networks on the internet, networks that implement ROV, to drop that announcement. So we're gonna see also how much time it takes for them to drop that. And we do that daily, and we've been doing this for about a year. The timings we record are first the timing when we ask the RIR to create the ROA. We also obtain some timing from RPKI view. RPKI view is an archive of RPKI data. So they are like taking snapshot of RPKI data, so we can see when the ROA we created appear there, or when we delete it, we can see when it disappears from there. And then we look at BGP data. For that, we use RIPRIS. We're going to see when our prefix is reachable or not. And we also did some traceroute measurement from RIPE Atlas to see if it corroborates with the BGP data. This table here gives summary of the result we had when we create a row, so when our prefix become valid. The numbers in the table are all in minutes. The column shows different steps, so it's kind of like the different step we had here in the figure. And the line shows the different RIRs. We saw differences in the RIRs. So the first column is the signing time. When a row is created by the certificate authority, there is a timestamp in the row that tells us when the row was created. And we found that this timestamp usually match our querying time, so there is almost no delay. And when we query the RIRs, they usually create the row. The exception here is APNIC. We found that APNIC on average has about 10-minute delay. And from the data, we could understand that APNIC has a 20-minute batch. So they receive queries for an interval of 20 minutes. They process all of them, and then they wait again 20 minutes, process all of them. So we can see that batching already had 10 minutes of delay. And we're going to see these 10 minutes. Of course, like that's going to be all this delay accumulate, so it's going to be visible all the way along. I will skip the note before. The publication is when the ROA is made available on the repository, and we usually see that the ROA is available a couple of minutes after the creation. The main outlier here are ARIN and LACNIC. So during our experiment, we found that there was a bug with ARIN and LACNIC. They were creating ROA with a wrong not before timestamp, and that was preventing the ROA to be published in time. We saw a delay of up to 5 hours for ARIN, and on average, we saw a delay of 1 hour. We've reported that to both RIRs, and they could fix it quite quickly. So this is not something, it's not a problem you should encounter anymore. So if I remove the outliers, and if we just look at Afrinic and RIPE, so it takes only a few minutes for the publication. And then we saw that it takes another 10 minutes about for the relaying party to fetch that data. This is the longest, the step that have the most delay. And then it just takes a couple of minutes to see this on BGP. So the main takeaway here is most of the delay we see, apart from like the bugs and the batching we've seen with APNIC, comes from the slow pooling rate of the relaying party at ISPs. This is now the summary of the delay when we delete RAW, and the results were quite different. That was a bit surprising. So for APNIC, we had the same batching that happened. So we see this 10-minute delay in the revocation. Revocation is the RIRs keep a list of ROAs that are revoked. And we can see that usually the revocation happens just when we ask them to do that. The relaying party are a bit, it's the same order of magnitude, about like 10-15 minutes. And but then we see it takes a lot of time to see the change in BGP. It's about like twice slower to see the change in BGP when we delete ROA. And for that, the main explanation for that is that a lot of large ISP gonna use multiple relaying party to ensure resiliency, so they don't rely on only one single party that is running. But that means when we delete a ROA, all the relaying party that they're using, they all have to delete this for the router to take this into account. So that's going to be the slowest relaying party that will always penalize here the delay. So we found that deleting ROA takes quite quite more time than creating one. We could dig a bit more into the result, and we could see like this is the detail for our upstream provider. The x-axis here shows the delay. The different colors show the different RIRs. So the red and the light blue one are Lacnic and Arene. So you can see they are quite different because of that bug we reported to them. Epinic, you can see that shift of 10 minutes. And we found like there was like a few cases where it took a lot more time. What was interesting in breaking down the result here was that for one of our upstream, we saw that the deletion took a lot of time, and we investigated that with them, and we found like there was another bug in the relaying party, so they could fix that also. Okay, so that was just an overview of that study. There is quite a lot more result in the paper. We published this in PAM 2023. So please take a look at the paper if you're interested in this. And this is the conclusion of my presentation. So we just designed and set up an experiment to measure RPKI delay. We've reported issues to 2 areas and 1 tier 1 network. We found that RPKI is order of magnitude slower than BGP, and so that might have some impact on the network for network operations. The only recommendation we can really give is for ISP to try to pull RPKI data a bit more frequently. And that's it. So here's my email if people are interested. Thank you very much.
Thank you, Romain, for your presentation. Do we have questions for Romain, either from the audience or from the panel itself? If not, I have a quick question for you, Romain. So you talk about the main bottlenecks. Do you think the operators can adjust some knobs to speed up a little bit the propagation of RPKI
yeah, sure.
objects? Mm-hmm.
Yeah, so because in RPKI, like most of the data is pushed. Like for example, here the operator like just push this to the portal, and the portal push it to the certificate authority. It's pushed to the publication points. And the only place where and in BGP it's same, like all the data is pushed, so that's why it's quite fast on BGP. The only time where the software has to go to a place and fetch it is for the relaying party. So that's why those relaying party, they are set like to fetch data every 15 minutes or so. Speeding up this pulling time can speed up the whole process. And it seems that we don't want to, of course, overload the areas, sending too many requests, but this was already more or less planned in RPKI. Like there is 2 protocols to fetch the data. So rsync is the slowest one, but for the other one, it's gonna just give like difference. Every time there's a change, it's gonna give the difference, so it shouldn't overload too much the areas. And that's what we heard from areas also. They said like they don't have problem with scaling, so it seems to be a recommendation we can make.
Mm-hmm. Great. And I see Tom Harrison from Epinic has just put a note saying that Epinic is now signing ROAs when they are submitted. So okay. There's no batching made. So that's interesting.
That's something I wanted to add to. Yeah, like we did that study, so it's now like almost 2 years ago, and things have changed already. Things are changing very quickly in RPKI. Even like during the study, we've seen relaying party software that get updated, some bugs that are fixed. So as we were measuring things, we saw already that things were changing. This presentation has been made at the AETF RIPE meeting, and there was a good good feedback from Epic also, like they said like they're trying to fix a lot of this. Yeah.
Excellent. Thank you, Romain.
Thank you.
Great. Great. So this transitions well into the next talk from Zubair, who is also going to talk about timing issues, but mostly on the validator side of things. Over to you, Zubair. You can start.
Thank you, Amreesh. Hello, everyone. I'm Khwaja Sediqi. I'm a PhD student at Max Planck Institute for Informatics based in Zubair, Germany. I'm in my third year of my PhD. And today I will talk about one of the research projects that we initiated together with Romain and Amreesh, part of MANRS research fellowship. The title is an analysis of RPKI validation time. So it's a good, timing-wise, it's a good follow-up to Romain's presentation. This research we started last year, so I joined as a MANRS research fellow, and then it's a joint effort with Massimo, Romain, Amreesh, and also Max, supported by MANRS, obviously. As Romain discussed, the time factor in the RPKI validation is becoming more and more important. People are adopting RPKI, and that's why it becomes important to have a smooth operation of the RPKI, as well as it's also delegated to other operators where they can host. So we think a smooth operation and also a fast operation of the RPKI entire ecosystem and the validation process becomes crucial. And this study, actually, it's slightly the other opposite of what Romain did. So there we explained flight time. Here we try to see, can we identify the delay components in the RPKI validation process? And if yes, can we have some recommendation to the community on where to optimize it? So we tried to address this problem. What we did for our methodology, we used VM, and we tried to validate the RPKI data, several iterations for a period of several days. We do it in online mode, where there's nothing in the RPKI cache, or the validator cache, or the relying party cache. And then we fetch everything fresh from the network. And then we do a second run or a different run in offline mode, where we have everything available and we try to validate it again. Apart from that, we also try to understand how much the depth of certificate chain, the deeper you go in the RPKI ecosystem, can affect the validation time when you do the validation. We used RPKI client and routinator as a relying party softwares for our analysis for this particular task. After this section, we try to understand in which regions in the internet, like globally, there is more delay towards reaching the URLs or the RPKI URLs. And for that, we use the RIPE Atlas anchors. We select anchors particularly because mostly RPKI validation is done by network operators, and these anchors are well connected and hosted in these network operator setups. We try to see, is it really different if you're using IPv4 or IPv6 as a source to reach the RPKI URLs or TAs trusted anchors? And is there any difference between the trusted anchors and the trusted anchors that are hosted not by RIPE, but other network operators? And lastly, we also try to see is how much is the difference if you're using RRDP as a primary protocol or rsync for RPKI validation. I mean, right now, most of the relying parties, they use RDP as the primary protocol to fetch the RPKI data, but they fall back to rsync if the content is not available on RDP. So yeah, but first let's have a look at the RPKI validation over time. Historically, how does it look like? I mean, we use the data from a period of time from beginning of 2020 till February 2023. And here in this plot, the x-axis is the date, basically almost a year and 2 months. The y-axis shows the times, which is for all blue lines. And the green lines shown in bar are the number of validated payloads or VRPs. As you can see, the number of VRPs are increasing. It was more than 400,000 by February 2023. And the validation time varies. There is some time, so you can see that there are peaks. It's a structure sample for some particular repositories, but generally the validation time also has increased. However, one can notice that there is a lot of updates and patches added to the relying parties as well during this time, and they are upgrading it regularly, and also there are changes on the repository sites. But how does the data look like? So if we turn RPKI data into numbers, how does it look like? In this plot, we try to show what is the numbers within the RPKI dataset. So on the y-axis, we show the percentage or the share, and on the x-axis, we show different components or different attributes. And we try to split it for all the 5 years with 5 different colors. As you can see in the plot, the number of certification CRLs or certificate revocation lists, manifest, failed manifest, and all the other parameters, including IPv4 and IPv6 VRPs and autonomous systems here. The right one is dominant. Basically, right contributes to the largest fraction of the RPKI data. It's followed by UPNIC, shown in orange for most of the components, and also ARIN in green. And yeah, the LACNIC and AFRINIC contribute to the smallest portion of the RPKI data that we validate. But if you look at the validation for all of these different rares, how long does it take to validate a VRP? For every different TALs or TA, trusted anchors. In this plot, we did a iteration of more than 100 on the y-axis, and on the x-axis, we show the number of VRPs per millisecond. The 2 plot, one is online mode, where there's nothing in the cache, and we try to fit all the content from the repositories. And on the right plot, it's offline mode, where everything is available in cache, and we just try to revalidate the cache, basically the data that's available. So the idea was, do we observe any difference in the validation time between different TAs? And as you can see here, the red one and the blue one, which is APNIC and RIVE in the online mode, per millisecond, it has like the double number of VRPs. So in short, one can say that for APNIC and RIVE, we can validate double number of VRPs in the same time, and then comparing to the LACNIC and ARIN, and it's even triple than the VRPs from AFRIN. But one could argue that yes, because you're using online mode, so it could be that those destinations are far from the location you're validating it. That's why we try to do a cross-check in offline mode, where there is no influence of network connection. The data is locally available, and then we try to check again how many VRPs we can validate for different TALs using the same software or relying party software. Here, the scenario is similar, it does not change. And again, the RIVE and the APNIC one, you can see that it's almost 9 VRPs per millisecond. However, for the other one, it's less than 5, and for APNIC, that's even smaller. So basically, the APNIC and the RIVE has a higher number of VRP validation in shorter time. But the question is, what could be the reason for this? Why is it like that? And we try to understand it. So we look at it how these regional internet registries how they do the publication of VRPs. For that, we checked the number of VRPs per row of file, as you can see here. So in this plot, we try to show the average number for an iteration, 100 or 100 plus iterations that we did over 3 days. What you can notice here is that the red and the blue, they have more than 5 VRPs in a single row of file on average. It means that both Apnic and RIPE, they are bundling several VRPs into a single row object or file, and then they publish it. However, for the others, it's either near to 2 or less than 2. And for some of them, like for this one, for Afrinic, it's even smaller than 2. So it's probably there are a lot of duplicates or same provides a lot of invalid row of files that we get from them. To ensure that our results are correct, on the left plot, we checked it with RPKI client, but also we tried to do this similar analysis using Routinator software, and the result does not change. So the main takeaway from this one is that bundling several robots helps in the validation process and reduces actually the validation process. Next, we tried to check how much depth of the certificate chain can affect the validation time. For this analysis, we did it for all the 5 tools or main tools. And here we do it in 2 modes. The bottom one is the offline one, and the top is online one. But let's first have a look at the online one. So on the x-axis, we show the time it takes. And on the y-axis, we show how deeper you go in the certificate chain, like from the main repository. If you go down, how does it affect? And the colors here show the number of VRPs shown in the top legend. So when we can easily notice that the color here changes from green to red. And if you look at the numbers, the difference between green to red is nearly like 2,000 to 3,000 VRPs. However, the time increases from 50 to nearly 80 or 90 seconds on average, if I call it. So what does it mean is that for the depth of certificate, there are, for example, 5% of VRPs, which is like 2,000 or something. This is particular case of ARIN that we observe. They contribute to 25% delay for that particular tool. So there's a small chunk of VRPs hosted somewhere in the certificate chain. If you fetch them, it adds like 5%, but it has 25 to 30% delay. However, if this is not in the online mode, if you just do it offline, which is available for you locally in your machine, then that effect is gone, and you can see it just becomes flat on top of depth of 3. After this analysis, we try to look at globally from which regions the RPKI URLs or tools are poorly visible or has a higher delay for reaching them. For this experiment, we used, particularly we completed for RDP, but we are also doing it for rsync. For all the tools or URLs of RDP protocol, we run a TCP-based trace route from all the anchors, and we do it for a period of 1 week every 5 hours. And so the idea was to see in which regions the RPKI tools or the URLs of all the URLs that you would need to fetch data from is having how much delay if you look at globally. And here, for the interest of time, I will show one of the results where we measure for IPv4 versus IPv6 the delay globally. And as you can see, generally, if you have a first look, the result is very similar. It means that both IPv4 and IPv6 in terms of delay, they have a similar results. However, in terms of regions, if you zoom it in, the dark blue, which has lower RTT, like 80 or less than 100. So these regions in US, Canada, Europe, they have a shorter RTT to reach the destination. And it's true for both versions. And some regions, for example, this region, India or Pakistan, or some regions in Africa, they have a higher round trip time to reach to the destination. And this is true somehow similar for both IP versions. There could be some slight differences. This is specifically clear for the case where this country on top of China, I think I'm not sure about the name, but probably Mongolia, or I don't know the name. But this particular country has a higher delay if you use IPv6, so it's more than 200. But if you're using IPv4 in this region to reach the toll, it's 150, I would say, on average to reach all the RPKI tolls. And yes, with this, I will conclude some key findings of our analysis. So we show that bundling several VRPs into a single object or raw file reduces the validation time for the relying parties. The depth of certificate chain has an impact, but it should be clearly set up so that it should not affect the entire RPKI validation system. And while the trace route for IPv4 and IPv6 towards RPKI tolls are similar, certain regions, they observe more delay in this RPKI validation for RTT time. That's it. This project is still going, so it's still work in progress. And feel free to reach out via email or LinkedIn for further communication and questions. And I will be happy to take your questions. Thank you very much.
Thank you very much, Zubair. Do we have questions from the audience? I don't find any so far. Zubair, thank you for this very interesting presentation on the different timing parameters that basically affect timing of validation. Maybe a quick comment or question. So you mentioned that the more we have ROAS, and so this increases the validation time. But at the same time, there is also an RFC, I think it's RFC 9319, about the use of max length, where basically they do not recommend the use of max length, and basically it tell operators to create as many ROAS as possible for the operations, and this goes, as we see, a little bit on the contrary here, because it would increase validation time. So eventually, yeah, maybe operators will have to make a balance between time and security. So yeah, thank you, Zubair.
Thank you very much, Amreesh.
Great. So, and then finally today we have Thomas. Thomas is going to also talk about a very interesting and perhaps timely topic about forged origin hijacks and a system that he developed. So over to you, Thomas.
Thank you, Amreesh. Can you hear me well? It's all good?
Perfect. Yeah.
Good. Hi, everyone. Yes, I'm Thomas Holterbach from the University of Strasbourg. I am a postdoctoral researcher there. I'm also a 2023 MANRS ambassador, as Amreesh was saying before. And actually, part of my research is also funded by the ISAC. So today, I would like to show you how we can better detect forged origin hijacks. But as a quick introduction, let's just take this very simple example where we have a sort of a mini internet with a few autonomous systems which are connected using peer-to-peer or customer-to-provider relationships, and say that IS9 announces a prefix 9/8, so that prefix propagates through the mini internet so that every AS can reach the destination with a different IS path. That's how BGP works. Now imagine that there is an attacker, IS6, which hijacks that prefix. So the hijack route will propagate through the internet, and some of the ISs, the one actually which has the shortest path towards IS6, will divert the traffic to the attacker. Well, you probably know that there are some defenses against BGP hijacks, so that's a good news. So for instance, you can use protocol extensions such as RPKI plus ROV, BGP sec, ASPA as well. You can use configuration guidelines as well, such as route filters. And finally, you can use monitoring platforms such as Artemis or BGP Alerter. Well, this is useful, but despite these efforts, BGP is still today vulnerable to forged origin hijacks. So this is the particular type of hijacks where the attacker prepends the valid origin to the AS path such that the hijack route appears to be a legitimate route. Okay, so this is what happens in this scenario. So the hijack routes propagate through the internet and the origin is valid. The drawback of such an attack is that the AS path is slightly longer, so less traffic will be diverted to the attacker. However, in this case, the impact is still quite significant because we have like 4 ASs, AS 1, 3, 4, 7, that are still diverted the traffic to the attacker. And the bad news is that, well, the existing defenses, they actually poorly neutralize those hijacks. Why? Because RPKI plus LOV actually cannot detect forged origin hijacks. BGPsec and ASPA, they will probably take years to be deployed if they are deployed at all. Route filters, they are often missing and inaccurate. And finally, Artemis and BGP Alerter, they are kind of narrowly focused because they could detect type 1 hijack, but only the one that pertain to the IS deploying the system. Well, this is actually a problematic because forged origin hijacks, they are actively used by attackers. So for instance, those are just 2 examples that we found in the news last year. So in both cases, the attacker managed actually to steal money by attacking crypto exchange platforms. And in both cases, this was made possible using a forged origin hijack. Okay, so today I would like to introduce you DIFO, which is a system to detect forged origin hijacks, and it does it on the entire internet. So this is particularly useful to study those hijacks, to actually detect them such that we can take countermeasures such as deploying route filters, and also to profile hijackers such that maybe we can blacklist them, for instance. So the outline of this presentation, so first of all, I will explain you the main challenge that we have to address here. And then I will show you the key ingredients that we use. And finally, I will show you that our system is accurate and practical for users. So let's start with the main challenge, which is to actually detect fake AS links. So why this matters? Because when an attacker launches forged origin hijacks, well, this will very likely create a new AS link and a fake AS link. Okay, so if we take the previous example where AS6 hijacks AS9, well, you will actually you can use some of the BGP vantage point and the BGP data that are collected by those vantage points. So for instance, the collector, the RIPE RIS route use collector. So you can see the BGP route using those vantage points. And then you will actually realize that AS6 and AS9, they appear directly connected, right? They are consecutive in the AS path. And this is actually a fake link. Okay, so the victim and the attacker, they are directly connected, and that's a fake link. This link actually does not exist. Those 2 ASs, they are not pairing together. It's a fake AS link. And actually, an attacker can hardly escape from creating a new AS link when it launches a forged origin hijack. Well, it could do so, but in that case, it will really reduce the effectiveness of the attack. So for instance, in this particular case, AS6 could prepend 6759, in which case it is actually an existing path in the topology, so it would not create a new AS link. However, then the AS path would be much longer, and none of the ASs would actually divert the traffic to the attacker, so the attack would not be effective at all. So the problem, however, and the challenge is that there are many new AS links that appear every day, but there is no simple property that tells whether they are real or fake. So for instance, we actually count that there are around 166 new AS links that appear every day, and probably the vast majority of them, they are legitimate, and only a few are suspicious. And this is actually the goal of DIFO, is to be able to discriminate whether new AS links are fake or real. So now I will show you how default does it. And it does it using two key ingredients. The first one is a carefully selected set of features. And the second one is a balanced sampling. So to understand how those key ingredient works, let's take a look at an overview over, the default's IceLink inference algorithm, which actually comprises 3 steps. So the first step is just to find new links. This is actually pretty straightforward. We have vantage points, like the RIS, the route views vantage points. So we can see like BGP routes, we can build the AS topology, and then we can detect new links. So for instance, in this example, we have 3 new links, 2 are legitimate, 1 is suspicious. And then for every new link, we compute feature values. So here we use different categories of features. First of all, we use topological features. So topological features, they rely on the fact that the AS topology exhibits a particular pattern, like a hierarchical pattern where there are a few ASCs at the top and a lot of stubs at the bottom. So when there is a new link that appears, those topological features, they check whether this new link fits into that structure or instead if it kind of breaks that structure. Okay, and if it breaks the structure, then it's a sign that it's a suspicious link. So we use different topological features to capture different sort of changes. I'm not going into the detail here, but that's basically how it works. Then we have peering DB features. So here, what default does is that it actually leverages the correlations that can be found in the public peering information. So for instance, 2 ISCs that peer, they are very likely to share peering information. For instance, they might be connected to the same IXP, or they might be in the same country or in the same facility. And the other way around is true as well. 2 ISCs that are not supposed to peer together, they are unlikely to share peering information. So for instance, in our previous example, 6 and 9, they might be in different country and they might just not share any IXP or facilities, which is a sign that they are not supposed to peer directly together. Then we use another feature, which is the AS pass pattern feature. So here, actually default aims to detect fake AS pass, as they often violate the patterns that are induced by business relationships. So for instance, we know that the AS level topology, has this hierarchical structure. So if we take the degree of the autonomous system, which we have on the y-axis here, and if we take the different hops in the AS path, which we have it on the x-axis, then we should see something like this. So the degree should first go up, because we go up in the hierarchy, and then should go down. That's the case for a step-to-step path, for instance. For a core-to-step path, well, the degree just go down, that's obvious. But what we should not see is something like that. All right, if the degrees go down, then up, then down again. This is very suspicious as well, and we detect those cases. And finally, we have another feature, which is the bidirectional feature. This is just we just look at whether we can see a link in both directions. For instance, in one direction in an AS path and in another direction in another AS path. And this is actually a very strong indicator that this link is legitimate, because an attacker cannot fake both directions of a link. Okay, and those 4 features, they are actually the key ingredient number 1. Why? Because we carefully selected them such that they compensate between each other, because there can be many attack scenarios on the internet. So we make sure that for every attack scenario, at least one or a few of them works well. And if one doesn't work well, then the other will compensate. Okay, so once we have computed the features, the last step is to actually infer the hijacks. So what we have here is an inference model based on a random forest that we use to make the inferences. And we train this inference model using state-of-the-art approaches used for link prediction in graphs, which means that we actually take samples of existing and non-existent links. We compute feature values for those links, and we use them for the training. The problem is that if we just do that using what state-of-the-art approach usually do, well, it will not work well. Why it's not going to work well? Because when we randomly sample the non-existent links, well, it will make the performance of DIFO very skewed. Especially, DIFO will perform very well towards the stub-to-stub links and stub-to-stub attack scenarios because they will be overrepresented in our sampling. To illustrate this, we have actually clustered the different autonomous systems based on their degree and their cone size. So we have 8 categories of autonomous systems. We have the stubs, we have different transit autonomous systems, 1, 2, 3, 4. We have the highly connected one, the tier 1, and so on and so forth. And then here we show the proportion of non-existent links that are sampled for every pair of categories. Okay, and you can really see that most of the non-existent links that are sampled are stub-to-stub links. So if we just do this for the training, DIFO will work very well for this attack scenario, but will not work well at all for all the others scenario. Okay. So this is where we actually plug in our key ingredient number 2, which is a balanced sampling. So here we make sure that we really sample all types of links that exist between all the categories of ISEs. So for instance, stub to stub, tier 2 to stub, tier 1 to stub, and so on and so forth, to make sure that DIFO works well in all attack scenarios. Okay, so now we'll show you that DIFO is accurate and practical for users. So one of the challenges when evaluating DIFO is that we don't have grain truth. So what we do is we artificially create forged origin hijacks. And to do this, it's not very hard. We just take existing AS paths that we can observe from the BGP routes, and then we just prepend a new origin to create a new link. And then in some cases, we actually create a new link that exists. So that's a legitimate case. And in some other cases, we create a new link that does not exist. So that's malicious cases. And then we focused on the true positive rates and the false positive rates. Okay, and this is the result for the true positive rate. So again, we take the different categories of autonomous system. On the y-axis, you have the attacker. On the x-axis, you have the victim. And so we have all the different attack scenarios in these grids. And you can see that for all attack scenario, the TPR is always very high. Actually, the lowest TPR is 0.73, which is still quite high. And in terms of false positive rates, well, you can see that, again, for all the attack scenarios, the false positive rate is very low. Actually, the highest false positive rate is 0.15, which is still rather low. So what about the practicality of the system now? So what we did here is we counted the number of cases that are reported every month in 2022. That's the x-axis. On the y-axis, you have the number of cases. And first, we took a very naive approach, more or less what is done today, which is just to return all the new AS links that we observe. And if we just do that, well, we will get thousands of cases every month. So this is clearly too many cases to process by operators. But when we use DIFO, you can see that we can really reduce that number to a few, like tens or hundreds of cases. In terms of reduction factor, actually, DIFO helps to reduce the number of cases from between 7.8 to 22.4 times, actually. So that's the reduction factor we obtain with DIFO. Okay, so that ends my presentation. So I presented you DIFO. DIFO is a system that runs in a commodity server, but it can detect hijacks on the entire internet. I've shown you that DIFO is accurate in every attack scenario. Besides that, DIFO can detect past hijacks. So this is useful to profile hijackers, for instance. And DIFO also provides near real-time detection. So this is useful for operators to quickly take countermeasures. And finally, we have designed DIFO to be robust against adversarial inputs. For further information, I invite you to visit our website. It's still under construction. It's still an ongoing project. So everything is not really ready yet, but you can still get some information there. And we will also probably put like a paper on the website soon, so you can get more information about how it actually works more in detail. Thank you.
Thank you, Thomas. Perfect timing. So thank you everyone for keeping up on the time. Have a couple of minutes for questions if we have. We have any from the room? I see none. Maybe a quick question to Thomas. Do you have an idea of the percentage of photo-originating hijacks with regards to other types of incidents? Like, is it very prominent?
Well, it's hard to say because, in fact, we don't have ground truth. I suspect that still most of the cases reported by default are likely not forward-joining hijacks, but that can be ice-pass manipulation, which is still very useful to report for operators, such that they can take countermeasures or whatever they want. I think default, is also just, I mean, it's already useful today because operators, they just have a few cases to check every day, for instance. I mean, every month, actually, there is like, we counted that every month an operator would have to check maybe 1 or 2 cases in the million case. So it's almost nothing. But if you want to investigate further and really check whether the cases that are reported are forward-joining hijacks or not, I think we need to do more analysis. Like, for instance, we need to check whether the traffic was actually affected or not using data plane measurements. And we are also in the process of asking the operators some feedback if they find the output of default useful or if it's just like garbage for them. So, we are still in that process of understanding the reported cases by default. Actually, if in the audience, some people, they are interested. Well, I really invite everyone to look at the website to check the cases that involve their autonomous system. And if there are some suspicious cases, then check whether they are in fact malicious or if it's just false positives. And if you could give us some feedback, that would be extremely useful, actually.
Thank you, Thomas. Great. This sums up our MANRS research roundup. And as you can see, these are great research coming from our MANRS mentors and ambassadors. So keep an eye open on a future announcement of the MANRS program. It usually starts in June and the application starts in March. So there is a question, a poll, which is currently open. So please feel free to put some answers there. It usually helps us to improve on future editions. And I hope you enjoy the research talks today. And I'll see you hopefully in the next one, which is starting at the top of the hour at 13 UTC, which is about route origin validation research review. We have 3 excellent panelists as well. But if you're more interested in policy talk, we also have the working with government to progress routing security session at the same time. So a big thank you to our panelists today, especially Romain, who had to stay up late. Thank you very much.